Hi everybody, welcome to our video on continental collision and metamorphism. And what we're really going to do in this video is look at the story of how mountain ranges are built by continent-continent collision and how the rocks that are buried deep beneath a mountain range undergo metamorphic changes. And this is really important because it's these cycles of continent collision and mountain building that actually end up building the crust that we live on. This thickens the continental crust, which allows it to float higher above sea level and allows us a place to live. So in this video, we'll briefly look at the differences between continental and oceanic crust and what happens when you collide continental crust. Then we'll look at thrusting and folding, some of the mechanics of how rocks deform during a continent collision. And then we'll talk briefly about metamorphism and how deeply buried rocks undergo changes. So we'll start by noting the difference between oceanic and continental crust. Oceanic crust is thin and dense, and its oceanic crust is made mostly of basalt, which is much denser than the more felsic rocks that make up continental crust. Continental crust, in turn, is very thick, and it's also very light. It's much less dense. So as a result, the thicker, lighter continental crust actually floats up higher in the mantle than the thin, dense oceanic crust. So you can think of this maybe as being a block of styrofoam, a thick block of styrofoam that floats right up on top of the water. This may be a waterlogged stick that's floating really just barely above the water. And so the main take-home point is that because of their compositional differences in their thickness, continental crust not only floats high above the mantle, but it also floats well above the ocean water, giving us a place to live. Now we know that tectonic plates are always moving around on the surface of the Earth. And we've talked a lot about subduction zones, how that dense oceanic crust can go down beneath another plate and ultimately create volcanoes and then be recycled back into the mantle. What we haven't talked about is what happens when a thick, buoyant continental crust follows behind that subduction zone. And so in this example, I'll show you a video of India-Asia collision, in which India is effectively being towed towards Asia by the weight of this downgoing oceanic plate, and it's ultimately going to smash right into Asia and generate the Himalaya here. So let's look at this video. Boom. And what we're going to see here are some thrust faults starting to form, and then the Himalaya starting to pop out. So it's pretty amazing that the Himalaya aren't even that high compared to the thickness of continental crust. They're really just an extra little bump on top of that crust. And notice the collision takes place around 50 million years ago is when people think India first collided with Asia. It's still penetrating, and so the Himalaya are still actually growing to this day. So here's another view of that collision. Here's the before, and here's the after. And take a note of these thrust faults here. We'll talk more about this in a second, but these emanate from the actual plate boundary at depth. And what they're doing is actually ramping rock, being the Himalaya, up over other rock, being the Indian continent. And so these thrust faults have the effect of thickening the crust and also creating very high mountains. And now if we look at that from space, here are those high mountains. They are in fact the Himalaya. And the thrust faults actually run along the front of the Himalaya and are carrying rock upward out of the lower crust and uplifting it into these high peaks of the Himalaya. So we can almost think of these high peaks as being rock that's being squirted out between India and Asia as the two megacontinents collide. So let's look now more in detail at thrusting and folding. What are these things exactly? So thrust faults are one of the main mechanisms of deformation in a collision. They form when the stress is compressional, so when one continent is moving towards another. They tend to happen when weak rocks break. So in order to form a thrust fault, we have to first actually break the rock. And then we're going to slide one piece of the rock over and above the other piece. And of course, when we do this, when we thrust older rocks over younger rocks, we end up thickening the crust. So the crustal column right through here is now thicker than it was because we've piled one block on top of the other. And of course, as a result, that thicker crust actually floats higher in the mantle. And that is what we call mountains. And just to illustrate this, if we zoom in right here, here's an example of how a thrust fault places older rocks over younger. So you can see we've got these older kind of metamorphic basement here sitting above some of these younger sedimentary rocks. So older over younger can be diagnostic of a thrust fault. Now the other major type of deformation during collision is called folding. And this is where rocks would basically bend instead of breaking. And this happens in rocks that are usually basically able to bend. Obviously, if you're compressing a huge block of granite, like in the Sierra Nevada, that granite is so strong it could never fold. There's no way for it to fold. It could only break. But if you have things like sedimentary rocks that have layers, those are very prone to folding because the layers are able to slide past each other and provide planes of weakness that can slip and actually accommodate folding. We also see folds forming in metamorphic rocks, and I'll show you that in a second. Now, a little bit of folding vocabulary. If a fold is convex up, it's called an anticline. So here's an example of an anticline. If it's concave up, it's called a syncline. Okay, there's an example of a syncline. We refer to fold limbs as being the rocks on either side of the fold. So this would be one limb, and then this would be the other limb of the fold. And then we also can talk about a hinge line or an axis of the fold, which is basically a linear direction that represents kind of the crest of the fold. That would be called a hinge line. So here's an example of some of those small scale folds formed in a metamorphic rock. So this would happen when the rock was buried to a deep depth, high pressure and temperature, makes the rock ductile or gooey, and we can get a lot of small scale folds forming in what is now a very hard rock, but of course it wasn't always hard. Now here's another example of a large scale fold in sedimentary rocks. So this is the Sheep Mountain Anticline in Wyoming. And what we can see here is the geometry you get when you intersect a fold with the flat surface of the earth. So this is the same sedimentary bed right here, this white bed, and it wraps around in an oval shape. And so we can actually see that this same bed once went up and over the axis of the fold here. And so, but of course it's been eroded away. So we're seeing this kind of fold that's basically been chopped in half and exposed. Just to put that in terms of a sketch, here's a sketch of the same fold, and you can see here's a cross section from A to B, and we see those layers coming up and intersecting the surface where they've been eroded, and of course this layer would have once folded all the way up and over down to the other side. So that's a good example of an anticline that's been eroded to have this very unique oval look. So once we've had a big continent-continent collision, we've had faulting, we've had folding, what's the end result? Well, the end result is we get a much thicker crust. Okay, all these thrust faults have thickened the crust up. Ultimately, the subducting slab that caused the whole collision will actually break away, and sink down into the mantle. And then we think of these continents as having become sutured. They're basically now one continent, as if two cars had collided so fiercely that you could never disentangle them, and they became one big mass of metal. It's the same when two continents collide. They are basically now one continent, but they have this suture that forever records the collision that brought them together. And then, importantly, of course, there's a lot of rocks down deep here that are being metamorphosed. And those are going to record the pressure and temperature conditions of this mountain building event. So that brings us into the third part of the lecture, metamorphism and index minerals. So, as I just said, rocks that are buried more deeply obtain a higher metamorphic grade. And so we can think of metamorphic grade as being a transition from a rock that represents something close to its original sedimentary state, like a slate, into rocks that are increasingly more and more metamorphosed into something that really doesn't look anything at all like what it started as. So in this example, this would be a progression from slate to phyllite to schist and to gneiss. And of course, the slate is weakly metamorphosed, so it might be in a position near the surface that was hardly buried at all. The phyllites from a little deeper, the schist is from even deeper, and the gneiss is from the deepest level where it was almost melted. So how does metamorphism work? Well, a couple basic ideas of this. So we're converting one rock into a new rock, and we do this by growing new minerals. So we're going to, for example, minerals like biotite may become unstable, and their elements may get reworked into a mineral like garnet that is stable at a higher pressure and temperature. So some minerals disappear and new minerals grow, but importantly, the bulk composition doesn't change. So all the atoms that started out in the rock pretty much stay in the rock. So that composition doesn't change. We just get new minerals. Likewise, the growth of new minerals happens in a solid state. So these minerals don't melt necessarily. The atoms just rearrange themselves in a solid state into new minerals. And as I've already said, the changes in mineralogy are proportional to heat and pressure. So you'll get more new minerals as you heat the rock and bury it more deeply, and metamorphism becomes more intense. Now, one tool geologists use to unravel the growth and erosion of past mountain belts is this concept of index minerals. And the basic idea is that many minerals are unstable at high pressure and temperature. So as a rock is metamorphosed, those weaker minerals disappear and they're replaced by new minerals. And so as a result, the type of minerals you find in a metamorphic rock can be very diagnostic of the pressures and temperatures that it experienced, thus where it was buried in the mountain belt. So for example, chlorite and muscovite are really weak minerals. And so as metamorphism increases in this direction, they actually destabilize and break down. So for example, chlorite is not stable above maybe 300 degrees or 400, and muscovite's not stable above maybe 400 or 500. So they break down and they give their elements, for example, magnesium and iron or potassium, those get recycled. Perhaps, for example, these might end up getting recycled into garnet, which is stable at the higher temperature. Potassium may end up getting recycled into feldspar, which is also stable across a high range of pressure and temperature. So when we look at this, in sum, if a rock has been heated to high pressures and temperatures, it may have a unique assemblage of minerals. If you were to find garnet and selimanite and potassium feldspar, you'd know that your rock had been very heavily metamorphosed. But if you were to find chlorite and muscovite, you'd know that it had been very weakly metamorphosed. A couple caveats to this are quartzite and marble. These are really unique metamorphic rocks because their mineralogy really doesn't change. Both quartz and calcite, which makes up marble, are stable at high temperatures and pressures. So a quartzite might start out life as a quartz sandstone, and then it would become a quartzite, which basically still is nothing but quartz, because the quartz is stable across the full metamorphic range. Likewise, marble might start out as a limestone, which is also made of calcite. That calcite is stable. It might recrystallize and regrow, but ultimately the marble is only made of more calcite. So those are cases where the mineralogy really doesn't actually change a lot because the main mineral in the rock is stable across a wide range of pressure and temperature. So to bring this all together, we can look at a map view of New England. And this shows a map of index minerals. So basically, what is the highest grade mineral found in different places? And if we look up in Maine, the highest grade mineral is chlorite. That tells us right away these rocks weren't buried very deeply during mountain building events. But as we come down into New Hampshire, we see this is the sillimanite zone. Very high grade rocks that were obviously buried deeply and then brought to the surface. So we know that there's been a lot more thrusting and exhumation of rocks in this region than there has been in Maine. So that's how index minerals can be used. And then a final example is that geologists use faults, folds, and metamorphic minerals to reconstruct continent collisions all throughout North America and throughout the world. And this map shows the result of decades and centuries of this kind of work. Here's the outline of North America, and what's shown in different colors are basically the roots of different ancient mountain belts. So in red here is the roots of the Grenville mountain belt that was created by a series of collisions around 1 billion years ago. So there was once Himalaya-sized mountains here that are now gone. Here in the Yavapai Mazatal terrain, it was about 1.7 billion years ago that there was a Himalaya-sized mountain range through here that is now eroded and gone. And as you move into the interior of North America, many of these rocks record 2.5 billion year old continental collisions, very, very ancient collisions that first started to form the nucleus of the North American continent. So thanks for listening. I'll leave you with these concept questions and a quiz link, and see you in the next video.